Hi again, this is Tony Verbsky, trig teacher for online Metro Trig. Today we're going to do 9.5. We're going to introduce the unit circle, which is basically faster than a calculator for evaluating basic angles, multiples 30 and 45. But we'll start with today's lecture, lecture 9.5, with the word recall. Worst word in all mathematics, because we never do. Anyway, sine of theta is y over r. Cosine of theta, x over r. Tangent theta, y over x. And cosecant theta, r over y. Secant theta, r over x. Cotangent theta, x over y. And if you have a triangle, let's say it's positioned here, and you have some angle theta, and you're over x up y, you have some point xy, and you know x squared plus y squared equals, well, let's call this the radius of the circle, r squared. Because we wanted to study oscillatory motion, we added a variable theta and a variable r. We created these two relationships, sine and cosine, and then everything just kind of developed from there. Oh yeah, by the way, the radius is the square root of x squared plus y squared, and there's no such thing as a negative radius, therefore the minus went away on the plus or minus using the square root method. Now, while we're here, this is the opposite, this is the hype, and here's the ADJ. SOHCAHTOA helps us evaluate trig functions also. And CHOSHIKAO does also. So basically, these 6 things are the same as the above 6 things. Now, what we're going to do, we're going to work on our 30s and 60s and 45s today and all multiples thereof. So we can start with the triangle that we know, 1, 2, the square root of 3. By the way, the square root of 3 is like 1.73. This is the 30, 60, 90 that we all might remember from geometry. Now it does have an x, it's the square root of 3. It does have a y, 1. Clearly you have a radius and clearly you have an angle. So when I say sine 30, one way to do it is just memorize it. Sine 30, 1/2. Square root of 81, 9. Memorize that. Why not memorize sine 30? I'm in trig. But if you know your 30, 60, 90, you can get away with y over r, which is 1 over 2. You can get away with SOHC. Sine 30 equals the opposite over hypotenuse. So that's 3 different ways. Sine 30, 1/2. Memorize it. Sine 30, y over r. Sine 30. So, but we're going to go one more. Give you 4 ways. Now, what we're going to do is we're going to use the property of similar triangles where we multiply all 3 of these by 1/2. So we get this triangle that's smaller. 1/2. 1 square root of 3 over 2. And what we're going to do is say we're on the circle of radius 1. So we're on a circle of radius 1. The words radius 1 implies unit circle. That's all the unit circle is a circle of radius 1. But when I decide to evaluate it, and there is a new point, square root of 3 over 2, 1/2. See, this will work also. I don't need my original special right triangle. I can use any triangle that has a 30-degree angle in it. So when you go sine 30, okay, memorize it to be 1/2. Okay, next, y over r. The y value is 1/2, and the radius, of course, is 1. So it's 1/2. But really, when I ask you sine 30, and you're on the unit, the formula is just y. That's all it is. The formula is just y as long as you're on the unit circle. So instead of going y over r, like we just did, you just look at the y. Well, that y value is 1/2, therefore I'm done. Sine of 30, y value, 1/2. Now we're going to have this thing called a unit circle where it has a whole bunch of angles on it. And you just look at the angle, yell at the y value, and you know sine of anything that's on the unit circle. Similarly, cosine 30 was x over r, but now the radius is 1, so it's just x. So look at the x coordinate associated with 30, and you get the square root of 3 over 2. See, what happens if you're on a unit circle, 4 of the 6 formulas are now simplified. So on unit circle, sine theta will be a y value, cosine theta will be an x value, cosecant theta will be a reciprocal of y, and secant theta will be a reciprocal of x. But tangent is still y over x, and it's not simpler than it was before. And cotangent of theta is x over y, and it's just as bad as it was before. So the unit circle technically is going to make 4 of the 6 better. But if I modify it and give it a little slight tweak or improvement, I can make it work for all 6. So we need to learn how to build a perfect unit circle. So right now, see, we just have this guy right here. It's a 1/2 square root of 3 over 2, 1, and it's in the circle. And this is the 30. What I'm going to do is just kind of give this a kick, flip it up into here. And then kick it right here and spin it around. So what I have is the 60-degree angle right there. And this is 1/2. This is root 3 over 2. Of course, this is 1. But the point is 1/2 square root of 3 over 2. And I go sine 60. Well, on the unit circle, it's just the y value. So you just look at it and you write it down. Cosine 60. Just look at the x coordinate, write it down. Secant 60. Reciprocal of 1/2. Cosecant 60. Reciprocal of the square root of 3 over 2. So 2 over the square root of 3, making sure you get it right. Rationalize with the square root of 3, square root of 3, and you get 2 square root of 3 over 3. You can't, unit circle is the fastest, but the thing is, you need a unit circle in front of you to be fast. Now, when you get a little more experienced, like me, I have a unit circle stamped in my head, but it's still not as fast as having a unit circle like right in front of you, because you got to think about the unit circle. Therefore, it's like the world's fastest calculator. You know, we're going to be able to do like cosine 210. You just look at the x coordinate and you're done. So here's we go. We're going to build that unit circle, and what I'm going to do is take a whole page. Now you try to draw your best circle of radius 1. I am not going to try to be perfect in here. I think it's better that you can quick sketch everything anyway, it'll help you a lot in calculus if you don't depend on like having a whole arsenal of things sitting in front of you. So I'm a sketch on the fly guy. Anyway, mark your 1/2. That's the trick. Just mark your 1/2, because 1/2 was a special number. You just saw that it was twice. So you go up 1/2, down 1/2, right 1/2, left 1/2, left 1/2, right 1/2, up 1/2, down 1/2. And look what I just did. Perfect 30, perfect 60, perfect 120, perfect 150, perfect 210, perfect 240, perfect 300, perfect 330. Now, I need my points, because those are the things that you look at to quick yell out the value of sine or cosine. You know those 8 1/2 I just put down? You know where all the 1/2 go. Y is 1/2. You know X is 1/2. You know X is negative 1/2. You know Y is negative 1/2. You all know that this is the plus plus quadrant. Make sure your signs say that. And this is the minus plus quadrant. And this is the minus minus quadrant. And this is the plus minus quadrant. So that's the plus plus, don't worry about it. That's the minus plus, so there's a minus there. This is the minus minus, so there's a minus there. And this is the plus minus, so there's a minus there. Now you know the number that goes with 1/2 is the square root of 3 over 2. 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 Now, it's always nice if you mark the angles. 30, 60, 120, 150, 210, 240, 300, 330. You know what? It's always good if you write down the radian equivalent. So, pi over 6, pi over 3, 260s, so 2 pi over 3, 530s, so 5 pi over 6, 730s, so 7 pi over 6, 430, so 4 pi over 3, 300 is 560, so 5 pi over 3, 330 is 1130, so 11 pi over 6. It's nice to have all those, right? Just in case you ask a radian question. So, quick question, sine 210. Don't think, just look right there. It's the y value. Cosine 330. Just look at the x coordinate at 330, square root of 3 over 2. Does it make you smarter? No, not at all. Probably makes you stupider, but makes you fast, because you can evaluate all multiples of 30 and 45. No problem. By the way, here's 0. Sine 0. Look at the y coordinate, 0. Cosine 0. Oh, 1. So the 0s and 1s give you your multiples of 90. You can do 90, you can do 270, 180, 360, doesn't matter. So, you know what we're missing? Multiples of 45. So we're missing the angle between the 30 and the 60. We're missing this angle. We're missing this angle. We're missing this angle. We're missing the 2. Sorry, I was already down in the third quadrant. We're missing the 45. We're missing the 135. We're missing the 225. We're missing the 315. Now the 45 is pi over 4. There's 345, so 3 pi over 4. 225 is 5 pi over 4. My computer's a little slow. And there's 7 pi over 4, making this unit circle. Now I got to go down to the next page and figure out how to get a 45 inside my unit circle. 1, 1, square root of 2, 45s. So that's my special right. I use it on the job site when I was building houses all the time. Architects think they struggle with their 45-degree angles. I always checked 45s in their measure, and it turns out the architects were usually off by a couple inches. I don't know how, but they were. Anyway, this is the circle of radius, the square root of 2, which you may or may not care, but that's about 1.41. Anyway, I want to get this inside the unit circle, so I divide by the square root of 2, I divide by the square root of 2, I divide by the square root of 2, and we rationalize these two, and you get the square root of 2 over 2. Obviously, the square root of 2 over 2. So now that this has radius 1, we're allowed to plop it in. We go over the square root of 2, up the square root of 2. So what we're going to do is go back, and this point is the square root of 2 over 2. Is the square root of 2 over 2. And obviously, minus the square root of 2 over 2, the square root of 2 over 2. Now, don't get worried that my unit circle looks like crap. You got to understand, I don't even own one. I just make it when I need it. If you want a good one, make one yourself. I'm just like doing my thing, showing you how to make one. And if you're going too fast, hit the pause button. You know what I do, though? I go to the internet and print one of these off, find a really good one. But anyway, let's go to minus minus. I need to show off some apps. We're really slow here. So square root of 2 over 2 minus the square root of 2 over 2. Let me hit pause and shut down some things. Okay, I'm back. Now, I only got a little bit more to add to this unit circle of mine. So, what we're going to do is I'm going to go to my next page so I can do a little bit of work. There's room here. You know, tangent of theta is y over x. Now, this first, we got all these values here on the unit circle, like 0, 1. Oops, let's reverse that. Little 1, 0. Now, I know this y value is 1/2, and this is the square root of 3 over 2. This is the square root of 2 over 2, square root of 2 over 2. This is the y value is 1/2, and that's the square root of 3 over 2. So we know tangent of 0 is 0 over 1, which is 0. So there's a 0 there. We know tangent of 30 is 1/2 over the square root of 3 over 2. Now you'll get to where you realize that if you copy dot flop, and you get 1 over the square root of 3. But you'll get to the point where the second and fourth cancel, and you can still see the 1 over the square root of 3. So technically, you don't have to cancel that. And then you rationalize it, and you get the square root of 3 over 3. So that's the square root of 3 over 3. My favorite, y over x is 1. Same thing over same thing. Now, tangent of 60 is, you can't see it, it's 1/2 over, it's y over x. Oop, I wrote down the point wrong because I was getting the same thing. Clearly, x is 1/2, y is the square root of 3 over 2. So you get the square root of 3 over 2 over 1/2, the 2's cancel, get the square root of 3. And then this point right here, 0, 1, 1 over 0 does not exist. So what we're going to do is we're going to go 0, square root of 3 over 3, 1, the square root of 3 dne on our unit. So let's go up. And let me go back page. Just about used up all my colors here. I think we can squeeze it in. So this is 0. At the 30 is the square root of 3 over 3. This is 1. This is the square root of 3. And this is d n e. Now, we recall that all students take calculus. So we're working with tangent here. So all tangent, we know that tangent is negative in the second, positive in the third, and negative in the fourth. So you got the same points here as you do here. They're just off by a negative sign. So negative the square root of 3. Negative 1. Negative root 3 over 3. And finally, remember, 0 over negative 1 is 0. Same points there as there, but now they're positive, so root 3 over 3, 1, root 3. Negative 1 over 0, d n e. Tangent's negative in the fourth, so negative root 3, negative 1, negative root 3 over 3. Now, that's a perfect unit circle, but, you know, kind of messy. You should try to make one yourself. Like my daughter, she loves colored pencils. She's very organized. When she did this, by the way, now she's 20. She's actually in college, and she doesn't have any math left. But anyway, she made her own unit circle. Now, hopefully this works. It's supposed to do the whole desktop. So here we go. Let's do a search. Unit. Oops, sorry. I don't have a wireless keyboard yet. Unit circle. I need one really bad. Get my wireless mouse going. Now, there's only like a billion to pick from. Oh, let's not go that route. Let's go images. Now, if you look hard, you can see the one that has the square root of 3's marked all the way around. That's important. Maybe this one does. Nope. It does have radians and degrees both, and pretty good unit circle, but you want the one with the cheaters. You got to find the ones with the radical 3's around the edge. And oh yeah, look at all that cool other stuff you can look up. Hey, there's even video probably explain how they do that hand thing. Never really been a true fan. Moving along here. We'll find one. I struggled the other day. I teach this class at Highlands Ranch High School, and it took me a little while. Actually, kids were helping me. Tell you what, I think what we did is we actually searched farther. So we went unit circle with tangent. Images. So, ooh, here's one. It's kind of ghetto. Look at somebody actually hand marked them. Pretty good unit circle though. It'd work. This is better than mine. But there's a commercial ones too, so you can do better than that for sure. There's this one that's like pinks and oranges and light blues. If I run into it, it's got them on there. So there's one like super nice, cool one. But it's better that you like kind of go find your own and see which one you like, instead of having your teacher find your unit circle. You gotta remember, I don't even have a unit circle. I just kind of have it going on in my head. So it's temporarily gonna make you like super fast. I don't see it here, but you know, it used to be my favorite one back in the day. It has good resolution, but it didn't have the tangents marked. So I think you kind of know what I'm saying. If not, if you're going to force me, somebody say, please find a perfect unit circle for me, but I think you guys can do it. You guys are probably better online than me. All right, back to it. Sorry to kill some time there, but that's how I do it. Obviously, I need help. Look at this pretty unit circle here. Now, if you have your unit circle in front of you, somebody goes cosine 210. You just look at the x-coordinate at 210, but you guys know I don't actually have one. I know where 210 is, but I know y is 1/2. And the number that goes with that is the square root of 3 over 2, and it's negative, negative. And finally, I get to it, it's negative root 3 over 2. If you have the circle in front of you, you just look up the x-coordinate, you're done. Now, if somebody says secant 150, I turn and burn 150, and I know the y value is 1/2. I know the x value is square root of 3 over 2 negative. Secant's the reciprocal of cos, so I reciprocate that. Minus 2 over radical 3. Minus 2 radical 3 over 3. Whoa, rationalized in my head. Woo! Now, if somebody says tangent 30, you just look at your little root 3 over 3, and that's your tangent 30. Somebody says cotangent 60, if you have that, that's the square root of 3 for tangent. So therefore, cotangent is 1 over the square root of 3, which is the square root of 3 over 3. Once again, rationalized in my head. So once again, if you got a unit circle in front of you, it makes things extremely fast. You don't really learn anything, but boy, you can answer questions. So pretty good stuff. So let's evaluate that angle theta to be 7 pi over 4. That's 7/45, which is 3/15. So 7 pi over 4 is right here. The number is the square root of 2 over 2, square root of 2 over 2, plus minus. And let's just evaluate 3 of them. How about sine? Oh, by the way, theta. Boom. Right there. Pi value. Cosine theta. Boom. X value. Tangent theta. If you got it marked on the outside, you already know it's -1. That's how it works. It's a good day. It's a good day to be fast. Okay, so dare I try another one? Okay. I'm doing my reading here, trying to figure out what additional stuff they actually threw into your problem set here, because that's definitely a lecture. I mean, now it's just me looking at your book, and unfortunately I see a sun and a moon and the earth again. So we might have to learn something about distances. The moon is from the earth, or the earth is from the sun. I'm not sure. Don't feel like working that problem, to be honest. But I do see, and I hate that they use it. Here's example 5 on page 671. And they use cosine of S. Who uses S for an angle is, how about 1/2? Now, that's a unit circle number. One-half is. Now, cosine 1/2, you know, these are the 8 1/2. Cosine is the X. And all students take calculus, and cosine is plus plus, and this is plus, so it's got to be this angle and this angle. Therefore, S is 60 degrees, or S equals 300 degrees. Now, I can also work this problem another way. Cosine theta equals 1/2. Well, anytime there's an equals in math, when does this graph equal this graph? This is y equals 1/2 is the horizontal line, and this is y equals cosine x, or cosine theta. So if you memorize what the graph looks like, let's say on 360 or 2 pi, cosine is memorized to look like this. When does it equal 1/2? Well, here and here. Now, as you guys can tell, I am not the neatest grapher in the world, but it doesn't really matter. Sloppy or not, I'm pretty sure that's 60 degrees. And sloppy or not, I'm pretty sure that's 30 degrees and that's 60 degrees. I'm pretty sure it's 300. So look at me. I just guessed it with the world's worst graph. Uh-oh, lost my calculator. I was going to bring it up on the calculator, so here, let me show you what I'm working with here. I haven't officially created my calculator, finished my ROM image, so, you know, it takes a little bit to bring it back once I'm dumb enough to shut it off. Now, if you want to cheat, you usually cheat in degrees. So you switch to radians and you switch radians to degrees. Then you go y equals, and then you go sine, oops, that would be cosine, and you hit x. And then the other one is 1 divided by 2. Now I'm going to set my window myself, because I want to set my window. Now 0 to 360, let's go minus 90 to 450. Well, that'd be stupid to go every ticks of 1. 15 degrees is a really cool number in trig class if you're cheating like this. Now cosine is between minus 1 and 1 because I know what the graph looks like. So minus 1.5 to 1.5 graph. Okay, so from 0 to 360, we know where it stops. Now we're looking 1, 2, 3, 4. But so now we got to look at it. Now, if we're trying to find the answers from 0 to 360, what I do is I reset my window from 0 to 360. I like seeing the whole x-axis, you know, so I usually like go too far to the left, too far to the right, and then I actually set my window what it's supposed to be. Now, if you want to find that value, you see how I'm going by 15s. 15, 30, 45, I think it's 60, etc. We all know that's 270, and 2 more ticks is 300. But better yet, second calculate a point of intersection, number 5, and you just back that truck right on up. All you do is get it close, and you go enter, enter, enter. See how it's 60? Second calculate point of intersection. Okay, I gotta get a better emulator. I should be able to hold that button down. Hitting this button 58 times doesn't bother me whatsoever. I'm probably close enough already, but I'm gonna get it right on top of there and reward myself with enter, enter, enter. 300. It's called cheating. Effective. I've been doing it my whole life. It's a good trick. Anytime there's an equal, graph to left, graph to right, find out where they intersect. Unfortunately, in your book, they want you to solve cosine S equals 0.457 on 0 to pi over 2, which to me means on 0 to 90, because I know pi over 2 is 90. So if I were to cheat, I would go y equals to, now this is not a unit circle number, no way, 0.457. I would, whoops, 0.457. I would set my window 0 to 90. Negative 1.5 to 1.5 is really good because you know cosine's bounded between negative 1 and 1. Going by 15 is awesome. Graph. So it's going to take its time getting to 0 because you know cosine of 90 is 0. And it intersects right there. So second, calculate a point of intersection. Enter, enter, enter. So S equals 62 point. I'm getting old, so watch this. It's stored in X, second quit, hit the X, hit the X. I can see that better. 62.80630.824. Now there's two ways to actually get your radian answer. You can go times pi divided by 180, and you get the answer they're looking for, 1.0961767. You don't need a word to write rad, just don't put a degree symbol. So in this case, that's one way to cheat. Or the other way, you switch your mode to radians. You set your window 0 to pi divided by 2. Don't go by 15 degrees. You like to go by 15 degrees, but in radian format. Now we know 30 degrees is pi over 6, so pi over 12 is the perfect tick in radian world. And then the minus 1.5 to 1.5 is great. Graph. See, the graph is exactly the same. You just got to get used to resetting your windows, all your ticks and your units. And then we're going to find that it intersects. Sorry about that. Get it close. Enter, enter, enter. And of course, it gives you the radians. Once again, if we can't see that, you go second, quit, home screen, hit your X key because that's where it stored it. There you go. Now, does a book work it that way? Well, no, they don't work it that way because they haven't even graphed yet. So, finally, when does cosine S equal 0.45? Man, 7 is it? Sorry, 7. All you do is inverse cosine it. Like you actually understand inverses. Just go ahead and do it, everybody. And you type into your calculator in radian mode, and you go inverse cosine of 0.457. Oh, 1.0961787. Or you could be in mode. Switch to degree. And you do inverse cosine of 0.457. And you get the 62.80630.824. I hope I did a good job there. Once again, we will fully study inverses and all the issues associated with inverses. But it turns out at the angles less than 90 degrees, and that's where they put us, there is no problem with inverses. So go ahead, if you know the angle's less than 90. Inverse away. I'm at my 38-minute mark. Try to keep my lessons to around 40 minutes. You know, I added about an extra 10 minutes there, maybe 15. But I'm looking through the problems right now. And I don't know if I feel like doing any of them personally. I'm not going to do it. I'm not going to do it. There's this problem. So problems 57 through 66 on page 675, section 9.5. They got this unit circle type of analysis and this grid, and they're talking about the radians and all that. I'm not going to deal with it now. If it comes up in MML, I'll have a special little talk on it. like I say, I'm going to work your MMLs. I'm going to do one more lecture today, and then I'm going to just get cracking on your MMLs, because I like to work the problems too, especially the first time I teach out of a new book. You know, in first edition, oh my, we're talking, you know, problems, issues 1 out of every 20, 1 out of every 30. And once again, I will curb your math MML homework 3% for sure, and it might even go up to 5%, 7%, you know, since it's really the first edition, new book, reordered all the sections on us. I think that's all I'm going to do. Sorry about that. Let's stop it now.